start the segue today into hypothesis testing, which we're going to do then next time, I believe already. So we will continue today. So we're discussing today the normal curve, the standardization, and set scores. And next time we're going to start with hypothesis testing. So the rest of the semester is essentially going to be around hypothesis testing. So we have now the first 7 classes, we have discussed descriptive statistics mainly and the general topic of statistics. Now we're going to get really into inferential statistics. And while this is an introductory course and the methods that we're using are super simple, this is the basis of everything. So everything you're going to do in further statistical education is going to be based on this, what I'm going to teach you. So, okay. So let's do a quick attendance so we get this out of the way. Yeah. Are there any questions? So do you want to discuss the homework, or was that considerably clear what was being asked for? So essentially what I will be creating on mainly is a serious attempt at the problem. So it's like, I'm not gonna, if there's a typo somewhere in there, I'm not gonna take points for that, but it's essentially I want to see that you have really given this a try and that you really have given this a serious attempt. So, yes. Yes, yes, essentially the principle is that these sample quizzes that I give you, they're kind of in nature from the greater pool of questions. So I have this greater pool of questions that I have assembled. You get with each chapter, you get a sample quiz, which is a subset of that respective chapter pool. And then for the midterms, you get the greater pool. Okay. And then same for the final. Okay, it's all multiple choice. The midterm is all multiple choice. It's not all multiple choice, it's multiple choice, fill in the blanks, some calculations. You will have to calculate things. Is it open notes? Yeah. We can have our computer. Yes, absolutely. You need the computer essentially to take the quiz. It's going to be an online quiz only, so I don't do paper. Oh, the midterm's going to be on campus? Yes, yes, yes. Okay. Yeah. Yes. I saw you posted the solution to homework one, but yes. Are we going to get back our grades for it? Yes, yes, yes. I will go over the grades. Yes, I'll work on that. Yes, yes, yes. What day is in the grade? What day? That is 14th. Yes, so it's the 14th. Are there any conflicts? It's usually it should be considered what other midterms you have at the same time. So I think there's a schedule that comes from the dean's office. We could hypothetically do it on a different date. I don't really mind, but it is suggested to do it on that date. You had a question? Was there another question? No. All right, so let's do a quick attendance. So who came back already from the holidays? So you had a nice time? Nice time with your families back home? Good attendance. The Wi-Fi is still on break. Okay, Noah Abisidan. Hi. Adina Adler. Hi. Kayla Arshusadi. Hi. Eliza Balsam. Hi. Samantha Benjamin. Hi. Brooke Bloom. Hi. Hi. Daniela Botnick. Hi. Hi. Yehudit Cohen. Hi. Emily Dinner. Hi. Kira Elbaum. Yeah. Hi. Eden Elikan. Yeah. Hi. Shoshana Ellis. Yeah. Hi. Shoshana Epstein. Hi. Lauren Fishman. Yeah. Hi. Golda Goldberg. Hi. Emily Goldstein. Hi. Seema Greenberg. Nava Israel. Lindsay Kalish. Hi. Madeline Kastel. Hi. Kayla Mjodovnik. Hi. Haley Orge. Hi. Olivia Pella. Hi. Mira Postelnek. Mira?
Hi, I'm here.
Melissa Rosen.
Wait, Professor? Professor?
Daniela Rothschild. Hi. Daniela Samuels. Hi. Sophie Schanzer.
I'm here.
Eliana Siklik. Hi. Ashley van Emmerongen. Hi. All right, good. Okay, so today, as said,
Professor?
go into normal curves.
Hello?
And SETS course, we're going to do then hypothesis testing with SET tests on Wednesday. And this is going to be really where we're starting off. Then we have confidence intervals, effect size, and statistical power. I do this over 2 modules because it helps us to also review this, because this is very interconnected. Then we're going to do a lab day where we're basically going through some R exercises. That's going to coincide then with practice lab 2. Then we're reviewing for the midterm, and midterms is going to be 1 through 10. So this is going to be the midterms. You will see why I chose it that way, because we're getting right after the midterms, we're getting towards single sample t-test, and this is where the situation changes and things get a little bit more abstract in a way. But someone just asked to let you know that they're on stage. Yes. So hi, Mira. I've seen you. I have tagged you as absent because you're not here in person, but I've noted your Zoom attendance. Thank you. Okay, good. So much about the syllabus. So much about attendance. Then we had, so we have today a couple of files to download. We do have a PowerPoint presentation. That's essentially the lecture for today. Then we do have an Excel spreadsheet and an R code. Excel spreadsheet normal curve.xlsx is essentially a simulation that I have put together that basically shows you the arithmetic situation of a normal distribution curve, because essentially this is characterized with a mathematical function that allows essentially the estimation of the percentiles, as we will discuss them later on. The normal curve in R, this is an R code that basically illustrates the distribution curve. Then further, and then we have a data set that is the one from the lecture, that's the happiness report for different countries. Some of you may recall that we've seen the happiness report already in a bubble graph in the visual displays lecture. Okay, any questions concerning, okay, so what do we remember from the previous classes? So just as a quick recap. So we talked about descriptive statistics, right? So we talked about the introduction essentially to statistics, research and design, where we basically discussed statistics per se. What is the 2 different or 3 different mainstays of statistics, which is descriptive statistics, inferential statistics, but also the planning and design of research and the associated analysis. We have then talked next about frequency distribution, and this today is essentially a continuation of the frequency distribution discussion, because as you can remember, the frequency distribution, let's paddle back to the volcanoes. We've quantified for each country the number of volcanoes. We have that as a data set, and then we would basically transcode this data into how many countries do have 1 volcano, how many countries do have 2 volcanoes, 3 volcanoes, 4 volcanoes. And then we, so this is the so-called frequency table. And then we have, again, modified this and brought this into the format of a grouped frequency table, where essentially you build in groups. So we quantified volcanoes 1 to 5. How many countries did have volcanoes? Some were containing 1 to 5 volcanoes. Then we have further stratified this and calculated the proportion for each of these grouped frequency tables. So essentially what you're looking at was frequency distribution, and this is the characterization of the normal curve. This is essentially nothing else than a depiction of these counts. This is a histogram, right? So we have looked at this then in module 4 with the visual displays of data. where we talked about histograms, dot plots, violin plots, where we essentially have a box and whisker plot. You remember we have the box in the middle where we have Q1 to Q3, where Q1 is 25% of all the data is below that numerical value. Then we have Q3 where 75% of all this data is below this numerical value. That constituted the box. Then we quantified central tendency and variability, where we talked about the mean, the median, where the mean is the arithmetical mean of all the data, which is the sum of all entries divided by the number of all entries, where the median is basically separating all the data into two parts, 50% that are lower than that point and 50% that are higher. Then as the next aspect in that lecture, we talked about variability, which is essentially the depiction of this variability around the distribution. So we have a central tendency that is in the middle. We have the mean. And we have the distribution of the variability is characterized with two main markers that are of interest. One is standard deviation. And this is to understood how the calculation of this is conducted, which is basically you're calculating the differences of each individual entry from the mean. Then you square it, you sum all the squared deviations up, you build the so-called sum of squares. Why am I reciting that? Because the sum of squares is going to haunt you for the rest of the semester. It's going to come back with ANOVA. It's going to come back with regression. So the sum of squares will reoccur in your life. Good. And then dividing this by the number of entries. So we're getting the average squared deviation gets us to the variance. From the variance, we're employing the square root. We're getting square root variance is essentially the standard deviation, which is the variability around the normal distribution. That's important for today because standardization of the normal distribution curve is being done with standard deviations and the mean. And you will see soon what I mean. Then we also talked about the IQR, which is the interquartile range. Aforementioned Q1 and Q3 is 25% is below that point. Q3 75% is below that. The middle part between Q1 and Q3, the box in a box whisker, contains 50% of all your data points. So this is the middle part. So you have the ends to the side, which you don't care about right now. But basically the 50% in the middle, this is the beef of your normal distribution curve. This is where all the data is. Good, and this is quantified by the so-called IQR, the interquartile range. Then we talked about the ranges, which is min minus max minus min. So it's basically the range of all the outliers. And yeah, so this is a quick walkthrough. Then we have talked about sampling and probabilities. Understand probabilities in broad strokes. If you roll a die and you have you want to quantify the probability of having a 6, it's 1 over 6 is your probability. It's nothing to do with the numerical value on the die. It has to do with 6 sides on that die. If you roll it the second time, it's 1/6 multiplied by 1/6 as the probability for both of these events, mutually exclusive and independent from each other. Understand sampling, which is essentially the association between your sample and your population. So coming back from the die example, you have a population of New York City, and you know the prevalence, which is the technical term, the epidemiological term for the burden of a disease in a certain population at one certain time. That's the prevalence. This prevalence is for diabetes, let's say 10%. You randomly pick one individual from New York City. You have a 10% chance that this individual is a diabetic. Logically, right? Makes sense. So now 1 over 10, because 10% is 1 over 10 from 100%. If you want to sample now randomly from the population of New York City, good luck in that. It's virtually impossible. Well, you could go through a telephone book and just try to randomly find somebody from a telephone book, but random sampling is virtually impossible to do. Therefore, you try to create something which is called a sample, which is meant to be a representative subset of your population. So you sample a certain amount of people, You take 100 people out of the population of New York City, and you hope that you somewhat randomly sampled this sample subset from your population, and that the prevalence of diabetes in your sample is also 10%. And then you pick again one from the population, that should again be 10%. It's likely not the case because generalizability or external validity, as we've discussed it in module 7, is one of the major challenges of research, because we're sometimes just restricted to convenient samples. Yes.
I have a question not related to this.
Excuse me?
I have a question not related to this, but
Okay.
for the midterm, will we be doing a review, or will you be giving us an outline on the topics, or will we be doing a review in class?
You mean the review session? What review do you mean?
Review for the midterm.
Well, it's the syllabus. What do you mean review?
Like, will we be doing a review session in class, or will you be giving us an outline for what we need to know for the midterm?
Yes. So the review session that is module. That is module. So you want a list of keywords?
Like just a list of topics, or what you expect of us, or what the outline is for the midterm.
Well.
What are we going to be tested on?
Well, all of this. So we can in the review session. So I think I understand where you're going with this. Yeah, I don't see much value in giving you a list of topics, because it's essentially everything we discussed can hypothetically be in the sample quizzes. So all that I have discussed in class will in some shape or form be in the quizzes. So you will not really be able to avoid going through all the PowerPoints again and listen to the recordings
And
again.
then on the actual midterm, what's the format for it? Like, I know you said part of it is multiple choice, part of it is.
Yeah.
What is that?
It's the sample quizzes. If you do well on the sample quizzes, and these are meant to give you a taste of what it's going to be like to be tested on the chapter. If you do the sample quizzes with each chapter, you're in a good shape.
So, but it's a sample quiz, but it's not, the midterm is not on multiple choice, you said.
It's not all multiple choice. You remember how I talked about samples? So the sample quizzes is a sample of the greater population of quiz questions.
I know you said, like, if not all of it is multiple choice, how else are we going to be tested on the other part of the midterm?
Well, it's fill in the blanks. There will certainly be calculations. So what we will do today was standardization of the calculation of set scores. Expect that.
Okay, the calculations, like, we have to just get ourselves, like, there's not going to be any options.
Depends on the question, I would say. I think both is possible. You will see both versions. So something where you have to write in the numerical value, there are others where you just pick one. Please understand how to calculate it, because I've seen so many regrettable mistakes. Please really.
Will we use Excel to do the calculation?
Up to you. You can do Excel, you can do calculators, like non-discriminative.
Do you think it's easier one way or the other?
Well, I'm an Excel friend, but I would go for Excel by all means. I don't even know why calculators are still being produced, but there seems to be some value to them. Yep, makes sense.
Yeah.
So we will have a review session, and essentially this midterms is only covering 10 chapters, right? So this is not terrible. This is not that much. It is a lot of material now that you're coming freshly into statistics. But we have the review session. Just make sure for the review session that you have questions and like really challenge me on what you don't understand, that I explain it to you in a way that you understand it. It'll be fun. Don't worry. Okay, good. Syllabus. What else? Okay, sampling and probabilities. We want a randomly sampled samples that are hopefully a subset. But probabilities. I think that's enough of this. Okay, so let's get started. Okay, so the normal curve standardization on set scores. So the normal curve, we talked about it. It's spell-shaped curve that is unimodal, symmetric, and defined mathematically. It's the foundation of inferential statistics. So why is it important to keep in mind that it's defined mathematically? And I want to refer you now to that Excel spreadsheet. So defined mathematically, it's basically defined as a mathematical function. It's defined as a mathematical function by 1 divided by the standard deviation sigma multiplied by the square root of 2 pi.
What is this?
To,
What is this called?
This is the mathematical function for the normal distribution curve. This gives you exactly this distribution curve. And the reason why I'm showing it here is because I think it's important to understand how all these estimations in Excel are being calculated. Because
Complicated equation.
it looks more complicated. You find it essentially here calculated. You find it employed. So it's then Euler's number to the power of minus x minus mu. So x is the individual entry, mu is the mean, squared divided by 2 sigma squared. It looks more complicated than it is, but it basically defines this equation exactly. Yes. You don't need to know this.
You know how to stop, like how to.
No.
What's sigma here?
Sigma is the standard deviation.
Is what?
The standard deviation.
What is standard?
Yeah. Remember that there are differences in the notations.
Population of the sample.
Exactly. Population and sample. So in a sample, you have an S on SD for standard deviation, and you have a sigma in a population. You have for the mean, you have an M or an X bar, which is the classical way of depicting means and samples, and you have a mu, which is this guy right there, for a population mean. Will become important when we discuss hypothesis testing on Wednesday. Okay, so this is basically a simulation of this mathematical function that defines the normal distribution curve. You don't need to know the equation. I just wanted to show that everything is basically quantified arithmetically and mathematically, and all is basically subject to functions. All these calculations are basically defined as mathematical functions and can as such be used as a function. So, and the most important thing is the normal curve is the foundation of inferential statistics. What does that mean? We have descriptive statistics and we have inferential statistics. Descriptive statistics are describing distributions. Inferential statistics is where you use the property of a normal distribution curve, in our example, in parametric tests for drawing inferences, which is usually the comparison of either a sample distribution or a population distribution to gain insights into some dynamics or differences. So we do in this class only parametric tests, which means the underlying assumption is that we're looking at the normal distribution. If you continue your journey into statistics, you will also do non-parametric tests, which basically makes no assumptions about the nature of the distribution. We do one non-parametric test, which is the chi-square test, which is, I believe, chapter 17, which compares proportion against each other. Good. Sample size. Sample size is a term that I will be using quite frequently. Basically, sample size is the size of a sample, as the name implies. And it's super important in relation to the normal curve, because if the sample size is larger, so that means you're drawing more people from your population into your sample, your distribution will be more likely looking like a normal distribution. A population basically distributes quite widely, has extreme outlier, whereas your sample is less likely to have outlier. So a sample is more likely to look like a normal distribution. With a larger sample size, this distribution looks even more like a normal curve. Yeah. The closer it gets to the size of a population, it usually gets even more like a normal distribution. Also, the larger the sample size, when you think about it, just for a second, a conceptual approach to thinking about means. If you calculate a mean of a population and a mean of a sample, if you just draw 10 people from the population of New York City, and you want to know their average blood glucose levels or blood pressure levels, how likely do you think this will be reflecting the population mean of blood pressure or blood glucose? Likely not very, right? You will have a convenience sample, it's going to be 10 people. What if you sample 100?
A little bit more.
What if it's 1,000? The larger your sample size, the more likely your sample will reflect in nature of distribution, so variability as well as central tendency, the more likely it will reflect your population mean. Yes?
I don't know if this is different than the normal distribution curve, but can you say though that if you take a sample size and randomly select your sample,
yeah,
then it should represent the population?
It should not, or it should?
It should, no?
It should, yes. And that's essentially what we will be doing with hypothesis testing. So essentially what you do in hypothesis testing, you're grabbing a sample, you calculate your mean, you estimate a variability, which we'll discuss today, which is not the variability as a standard deviation, but standard error of the mean, which we'll get to later. And you compare the difference, the distribution of the differences from that sample to that of your population. And you calculate the probability that this is the same or a different sample, so that the mean is different from the population mean. So this probability is actually what we will quantify in hypothesis testing, and we get to that. But good question. So sample of 5, as said, doesn't look really like a normal distribution. Sample of 30 looks already a bit more like a normal distribution, and the sample of 157 looks somewhat normal, not really normal. It's also characterizing a sample as being a normal distribution or not. This is unfortunately not really exact science. It's a little bit, you visually inspect it and you kind of give a statement based on visual inspection. It looks like a normal distribution. Therefore, we assumed it was a normal distribution. There are some statistical tests where you essentially do look at the distribution and you test against the null hypothesis that this is not significantly different from a normal distribution in terms of distribution, but these are rarely used essentially. So it's debated whether they really are useful. Yes.
Are most experiments like the distribution skewed?
No, they actually, most tests do actually make, so particularly with larger sample size, if you're adequately powered, if you have a sample size of, let's say, over 30, and that's kind of this threshold by statisticians, everything over 30, you kind of get away with a parametric test, and you can assume it's a normal distribution. If you have small data sets, then it's getting a little bit complicated. But generally, yeah, you would assume a normal distribution above 30. So as the sample size increases, the shape of the distribution becomes more like a normal curve. Okay, good. Can you think of variables that might be normally distributed? Well, it's, again, many clinical characteristics, many biological parameters are normally distributed. Blood pressure, blood glucose, lipid levels, blah, blah, blah. They all are normally distributed in larger sample sizes. Then there are some that are not. For example, example of classically skewed parameter in our daily life are like the things like household income, right? So you have the 1% that have a really high household income, and then you have like the rest like skewed to the left, right? Or skewed to the right. So basically, they're all on the left hand side. Same story in biological parameters, classically inflammatory parameters. Somebody who's healthy does not have circulating inflammatory parameters. Those that are very unhealthy, they have high inflammatory parameters. So basically that's an example for non-normally distributed parameter by default. You know already they're not normally distributed. There are ways how to deal with that, and you transform them and you basically shape them in normal distribution. which is nothing that you need to know, but you log transform them. So you basically employ a log on them and you transform them into becoming a normal distribution. You don't need to know that. So thought experiment, can nominal categorical variables be normally distributed? What do you think? Can a nominal variable be normally distributed? So not really, right? Because when you have a nominal variable, you basically define how you arrange them, and you basically have to count on the y-axis. They're not, if they build a normal distribution, you have to artificially altered it, right? If you have a binary outcome, you have 0 and 1s. You have a count for 0 and this count for 1. And this is not a normal distribution. However, if you think again about the diabetics, and we'll get to that when we come to hypothesis testing, because you can do with the proportion of diabetics in your sample. If you randomly sample 100 different sample subsets, and you have now 100 different samples in front of you, and each of them has a proportion of diabetics, 10%, 11%, 12%, 8%, 7%, 13%. So you get a distribution of your proportion estimates from each sample. That is normally distributed. And you make this assumption it's normally distributed to use it for hypothesis testing. But generally, nominal variables are not normally distributed.
What ordinal variables?
Same story, right? It's not a normal distribution per se. You would need to kind of manipulate them on your histogram.
There's no equal.
Exactly, and there's no sequential order, right? Well, an ordinal you may say, but you don't have a numerically x-axis, so it's not really what you would generally consider a normal distribution. Okay, so now we're getting a little further. We're getting now to set scores and standardization. Okay, so normal distribution, symmetric, bell-shaped. Standardization is now a way to convert each individual score on your x-axis into a standardized set score that basically gives you the distance of any individual point from the mean, that is in the middle of your normal distribution, expressed as the number of standard deviation it's away from the mean. Oh yeah, I like the skeptical look. Okay, it's simple. It's not terrible. It sounds more complicated than it is. Okay, so if you have a mean of, let's say, blood pressure of 120, and you have a standard deviation of 15, your set of 1 is 120 for the mean plus 15. So you calculate the distance from the mean expressed as the number of standard deviation in between. So you have here set equals 0, that's 120. Set equals 1 is 135. Set equals minus 1 is 105. So it's 120 minus 15. So it goes in both directions. So it's as simple, right? It sounds
Standard deviation is always 15.
No, well, for this sample subset, you have a standard deviation of 15, you know that. And you're utilizing what you know about this distribution to characterize and standardize it in terms of a set score. And you're using this formula. So you're using the individual entry, the individual data point x minus your mean divided by the standard deviation. So set minus mu divided by standard deviation.
What is that symbol? 1 x minus.
That is a mu, that's a sigma. Mu is the population mean, sigma is the population standard deviation. So we are still dealing with populations at this point in time. We're not yet on a sample level. Okay. So essentially you can characterize using this the entire distribution curve, right? So up until the last outlier, you can basically characterize each individual point. You have a blood pressure of, let's go through that example, the blood pressure. So you have a blood pressure of 120, that's your mu. You have a blood pressure of mu of 120. You have a sigma of 15. A set of 0 is 120, right? So now if you want to go to 0 minus 0.1, minus 0.2. So this is now, okay, now I'm rearranging already, that's not good. Okay, so if we do, let's do it differently. Let's do 120, let's do 120 minus 1.5. So that's 0.1, right? So now if we calculate, let's make it easier. It's too complicated. I wanted to just create the in-betweens. No, but let's not. So we have now 15 as our sigma. So we're doing the x, which is now, so we're doing 105. Yeah, I'm coming the other way around. That's not good. Okay, so this is the x, that's 105. Minus your mu, which is 120. And we're logging that one in. And we're dividing it by our sigma. So that's our formula to calculate the standard deviation. It's as simple as could be. So it's essentially, so again, E8 is 105.
Why are we choosing 105?
Because it's exactly 15, so the standard deviation of 15 away from the
So that's
mu.
like one standard deviation.
That's one standard deviation away. Yes. So with 105, we're getting this value. If we're locking this in now with the dollar sign, we're basically locking in the mean and the sigma. So we have now x, which is 105, minus the mean divided by the sigma. So that's exactly that formula from the PowerPoint presentation, which is here. So this is this formula, right? So we're doing x, which is 105 E8 minus mu, which is $E $9. Excuse me? Divided by $B $2. So that's now -1. If we continue this formula now,
The sigma?
yeah, so it's
Negative.
it is negative. It should be negative. If E8 is 105, it's negative. Because it's 105 minus 120, that's minus 15. Divided by the sigma of 15, that's -1. So if we are continuing this formula and we're using a couple of different values now, we're saying, let's do 111. Let's do 98.
Why are you using these numbers?
Arbitrary numbers.
And you're using the same formula?
It's the very same formula, and you can calculate. You can calculate it the exact same way.
You just drag it?
You just drag it. So it's the same formula. So you get them from -0.6 minus 1.5 for 98 and 111. Yes.
And the reason I wanted to see is telling you, like, what are those numbers?
It tells you the distance of an individual point from the mean.
From the mean,
From the mean.
we do one above 120.
Yeah. So we have here the mean of 0. With everything greater than the mean is 1. Everything smaller than the mean is minus. There's a negative set score. And here we go.
What do you mean it's -1? Because some of them are smaller than -1.
Yeah, so if the formula is x minus mu, everything, once the x is smaller than the mu, it will be a negative value, right?
It won't, it could be less than -1. Like if
Yes,
it's negative
yes.
0.6.
Yes. It can be much more negative. It actually, usually you can follow it up until like, it actually, since the formula is an asymptotic formula, it should actually never approach 0. It should actually continue up until infinity. So, yeah. So you wanted a positive one. That's
What can you like define what Z is?
Yep. Well, it's an individual score and the distance from the mean expressed in standard deviation. You will see soon why this is important. So the positive example could here be like 125 is here 0.33. Yeah. So it's simple, right? It's arithmetically like a stroll in the park, conceptually a little bit tougher. And now we're going to continue to make this a little bit more visible why we're doing this. Okay. So this is now standardization. That's how you standardize your normal distribution curve as set scores. You're doing that by basically subtracting the mean of the population from the raw score. That gives you the difference. Dividing it by the standard deviation gives you the distance of that individual point expressed in standard deviations. Good. Intuitively, same thing. You basically have here a mean of 70. You have a standard deviation of 10. You have 10, 80 is then a set of 1. 90 is a set of 2. Each individual set of 1.5 is 85. Yeah, it's simple, right? Yes.
So if you calculate the standard deviation, every standard deviation like above or below the mean is like another Z.
Exactly. No, so the C's, you're transforming it. That's all you do.
How many like standard deviations are there in a normal distribution?
That's what I meant with the asymptotic function, right? So you can continue this ad infinitum, but it doesn't make any sense anymore. So it's like beyond 3, it's like, yeah. Yes.
When you see it's 1.5, that just means
Exactly. Arithmetic. It's the same arithmetic relationship, right? So this is the example that Nolan and Heinzen give. So it's you have a small dog and you have a big dog. The mean between the small and the big dog, that would be like, I don't know, like a terrier or something. So that would be the mean, and this is like a negative C and this is a positive C. And why are you doing that? And that's I like that, because essentially what you want to do is you want to compare apples and oranges. That's essentially why you do this standardization, because it allows you to compare things that can numerically not be compared, right? If you have a blood pressure and you want to compare the distribution of a blood pressure, the distribution of, I don't know, happiness score, you can't commonly compare that. But you can do that if you standardize your distribution curve in that fashion based on the characteristics of your individual distribution curve. Then you can compare that, and you can compare apples with oranges. So I kind of like this analogy. So in the same concept, you basically can also calculate backwards. So if you have a set score that you're interested in, spoiler alert, 1.96 will be a very interesting one, because that constitutes 5% in hypothesis testing, which is that probability everybody's after, because everybody wants to have a significant test. So 1.96, or that individual set score multiplied by the standard deviation plus the mean gets you back to the individual score, right? Logically, because if you have Okay. If you have an Excel spread here, so you have 98 and you have minus 1.466. So you use now minus 1.46 multiplied by your sigma plus your mean, you're back at 98, 98.1. Because you're just rearranging it, right? If you have x minus mu divided by sigma, and you're multiplying now the set with the sigma, this basically leaves is being removed, and then you just bring the mu on the other side, and you're basically back at the x, right? It's just rearranging the formula. So
Can you do another example of that?
sure. 0.33 multiplied by your sigma. Multiplied by the sigma plus the mean is now 124.95. The inaccuracies in the calculation is because of the rounding.
And the sigma.
Sigma is 15, yeah? No, it's multiplied by the sigma plus the mu.
Oh,
Plus the mu, yes. Because here it's x minus mu plus mu, rearrange it to the other side. Yeah, sure. Okay, good. So that's the formula. We'll get back to the individual scores. So now we're going to carry this further. So the set distribution is a normal distribution of standardized scores. It's the same distribution, right? Same value, same distance, same standard deviation. So the distribution is going to look exactly the same. It's just a numerical value on the x-axis is transformed. The standard normal distribution is a normal distribution of set scores. So now it's a set score distribution, not a normal distribution of the individual scores anymore. So you do that to compare apples and oranges. And yeah. So here's an example why that actually could be useful. So you want to characterize emotions in research. You do a psychological experiment, you have them fill out a survey, they're reporting all emotions that they have, be it love, be it fears, be it disgust, be it, I don't know, positive taste, I don't know, whatever. And then you want to compare this with the perception of fear and the perception of disgust. These are three different metrics, which you can't really, I don't know, you can't really do anything with those metrics. But what you can do, if you have individual entries for each of your participants, you can use these to compare all these three emotions to each other. So you're basically comparing apples with oranges. That's why I like that slide, because, okay. So now it's getting a little complicated. Okay, set scores clear. Okay, standard deviations, distance from standard deviation from the mean. So each of these scores does also, and this is where it's important now that you understand set scores, that the standard deviation that you use to calculate your set scores is calculated based on all these same entries and the distance of those from the mean, squared, sum of squares, variance, standard deviation. Now you're calculating set scores. And you also know that the normal distribution curve is a mathematical function. That hypothetically beautiful normal distribution curve, which you assume that you're characterizing now with your set scores, basically also allows you below each set score to quantify what percentage of your population is smaller than that individual set score. If you take a mean and you have a symmetric distribution, the mean splits, the mean and the median are the same, and it splits the entire population in half, meaning everything smaller than a set of 0 is 50%. If you go now one standard deviation to the left, it's at this point 34% less, so it's only 16%. Okay. So the entire normal distribution is 1. That's 100% of your population. This is defined by a mathematical function. This has a so-called area under the curve. I assume that all of you are comfortable with integral. You know that you can calculate everything that is under this curve. If you're splitting this in half, to the left, you're 50%. You're going now 1 standard deviation to the left, and you go to z equals 1. From -1 to 0, you have 34% of your population. If you have 50 minus 34, everything smaller than a standard deviation of -1 is the leftover 16%. And this is where you start to standardize it and characterize it. So this is called the so-called empirical rule. Yes.
This every normal distributed curve has these percentages.
Every normal is, this is the assumption. This is the assumed underlying normal distribution that you are working with, that you assume is correct. This is why it's important that assumption that your data is a normal distribution for a parametric test, because that's the underlying concept. So empirical rule, the rule by Chebyshev. Within 1 negative and 1 positive standard deviation around the mean, you're capturing from -1 to +1, 68% of your population. From -2 to +2, you're capturing 68 plus 28, close to 96. It's actually inaccurate, it's 95.7. If you go from 3 standard deviations, from +3 to -3, or -3 to +3, you capture 99% of your population. And this is how you have to look at standard deviations. If you see a research paper, you see a mean and the standard deviation, and it's adequately powered, and it has like a good sample size, you can estimate within that standard deviation how much of your population is captured from mean, -1 + 1 standard deviation. This is super important if you're reviewing papers, if you read papers and you really want to intellectually penetrate them, this is how you have to look at your table 1. Yes?
I just missed the numbers from negative what, like the percentages were.
-1 to +1, 68%. -2 to +2, 95.7. -3 to +3, 99. It's called the empirical rule, the rule of thumb. It was developed by Chebyshev, and it's also the 68, 95, 99% rule. So you will find different terminologies, but they all talk about the same thing. It's like this categorization of your population according to the number of standard deviations. Yes, please.
Why for the second standard deviation do we say 95.7 and not 96?
Well, that's Northern Heinz is saying 95.7 is measly. So it's 95.7. It's just, if you put 1 decimal, it's 95.7. If you take the decimal out, you're rounding it up. So it's just.
But also if I say like how much what percentage is in the second standard deviation, is it considered whatever 95.7, or is it like 14? Like how do you?
We're getting to that. Thank you for asking the question though, because this will be what we will be doing in 2 minutes. Because you can do that, it's a mathematical function. You can do that very, very accurately, right? So you basically
ask, like, what is the second standard? I mean, like, do I consider, like, let's say the second standard deviation is from -2 to 2? Is that correct? So there's like 2 standard deviations away.
Can you repeat the question, please?
Like 1 standard deviation away from the mean is 68% of the data.
-1 to +1, so it's 2 standard deviations. Yes. It's 1 negative, 1 positive. It's total 2 standard deviations. So within 2 standard deviations, you have 68% Within 4, you have
Okay, that's how.
95. Yes, sorry. Yes, actually, I should have explained that better. Good point. Thank you. Great catch. Yes, please.
This is true for all graphs or just for normal distributions?
This is just true for the normal distribution.
And it was 6 standard deviations, that's 99.
Correct. Yes, yes, yes. Okay. So transforming, yes. So the set scores tell you essentially how much or what proportion of your population is less than that value. If you assume the entire population to be 1, it not only tells you that, it also tells you how much is above, because if you calculate 1 minus the proportion that's below, you basically get everything above, right? So this being said, we're looking now at a PDF that is also in your module, which is the set score table. And you're not going to like this table, but we're still going to need to know how to use it. So that's the so-called set score table. It's a lot of numbers, but they follow, but they follow a very logical outline. So you have here on top, you have the decimals. It's the decimals of your set scores. You have vertically, you have the set score up until the first decimal. I know it looks terrible. Yeah, spare with me. So you basically you come from zero to minus 3.4. That's page number 1. You want to have minus 3.46. That's here. So basically you assume the second decimal comes from here. So you go in the respective row, then you just follow the row along until you have the second decimal. Simple, right? It's not terrible. Okay.
Is that minus 3.4 is on the right column, and then to get the second decimal, like 1 minus 3.42, it's just this.
So it will become very clear once you look here at 0, because 0 is 0.5. So that's the proportion of your population that is to the left on the histogram. So it's splitting the normal distribution in half. Everything smaller than that is smaller negative set scores. So essentially you are getting here, when we look for a set score of -1, this is 0.1587. So that's 15.87% of your population has a numerical value of numerical blood pressure smaller than mean -1 standard deviation.
This is just compare all different types of data that get used first.
So essentially, you're characterizing how is your population distributed, right?
Yeah.
So you want to know, okay, let's say you're looking at a research paper and there's a blood pressure mention of 120 and plus minus standard deviation of 15, you know that 105, and then there's an association with worsened survival at blood pressures less than 105. You know that 120 minus 15 gets you to 105, that 16% of that population will have a higher risk of dying.
You found 105 on there. What did you find on there?
No, that was just an arbitrary number from that ridiculous example I made up before. So you basically just go one standard deviation away from the mean to the left. Less than that is 16% of your population. If you go to positive, and this is the second page of the PDF, if you go to +1, you have 84.13%. That's here. And this is 1 minus 0.1587, because in the exact inverted way, you calculate 1 minus 0.1587, gets you everything greater than that. So 1 minus these values gives you the values that are greater than that. So it's just characterizing it from minus 3.46 of 3.499 to plus 3.49. And you will use that because we have talked about the interquartile range, right? Yes.
Why those specific numbers? Like minus 1.346.
You remember the function?
Yeah,
All of these are modeled with the function.
of the first function of the normal distribution.
So this function, and this is why I've showed you that function in the first place, because this function is integrated and you calculate that area under the curve. And then you just take the respective snippets that you're interested in. And that is the probability. Essentially, it's a probability. If you look at it on a probability, you have, if you're randomly sampling one patient out of that group from minus 3.49 to plus 3.49, you essentially have 100% risk, or 100% probability, or the probability of one, that that individual has a blood pressure between these two values, right? If you narrow it down, your probability of picking one from that group is smaller because you're narrowing down that range. Because here, this is where all the people are, and this is just where the outliers are.
So,
That's why this is a non-linear function.
can you explain the example again with the blood pressure?
So if you want to pick individuals, so it quantifying the probability when you define a certain range and you want an individual with a blood pressure in that certain range, and you randomly pick one person out of your population, you have 100% probability that you pick one if you take the very extreme SAT scores. If you narrow that down, your probability also gets smaller. Because the more narrow your range of interest becomes, then you only take like this little snippet. And that's a percentage.
If the range that we want is the middle range, then we have a higher chance of
Relatively higher.
like getting it right.
It's true. Relatively higher, you have a higher probability in the middle part, which is reflected here because you capture here from 1 plus 1 to minus 1, you capture 68% of your population. So you have a 68% probability to pick one between your two standard deviations, plus 1 and minus 1. And that's why this is so important, right? Because once we get to hypothesis testing, we're basically bringing this to practice, that probability. Good. Okay. So empirically, 68, 95, 99. Now we're getting further. And now we're bringing this into practice. So essentially, when you compare a sample to your population mean or to your population, you essentially use a general principle which is called the central limit theorem to relate sample to your population. You're doing that by assuming something else. So you're assuming now that if you randomly draw a sample of 100 or any size, any sample size, you draw a sample from your population, you get a mean, right? You calculate a mean from that sample. That is one mean. Now let's assume you put that sample back into your population pool and you draw another sample and you calculate again the mean. You get a second mean. You do that 100 times, you get 100 different means. And these different means allow for you to characterize the distribution of the sample means. And the distribution of the sample means are essentially giving you a more normal distribution. So it's more likely to resemble a normal distribution than the actually individual scores. So this is the happiness score from the countries. So we essentially, these are the individual scores. And now we're trying to build the segue into characterizing the distribution of the sample means. So it's random, it's random samples that you have drawn that give you one mean. So each of these points is actually an estimate of the mean. And this has a certain distribution. And this is where this distribution of the sample means is the highest. That's your best bet on where the population mean is. So you're trying to maximize the probability of knowing the sample mean. And this is also the general principle which we will need for hypothesis testing, because this distribution of the sample means can then also be characterized by the so-called standard error of the mean. So the standard error of the mean is basically the distribution of this hypothetical distribution of sample means. Practically, you have a sample. You have a sample and you know the mean, and you want to know whether this sample mean is significantly different from your population mean, or is it the same? Does it come from the same distribution? What you will be doing is you take the standard deviation that is given in the simplest of all use cases, and you will calculate your distribution of the sample means by calculating the standard error of the mean, and you will use this for hypothesis testing. Because hypothesis testing is done by calculating the difference from your sample mean to the population mean and standardizing these differences by utilizing the standard error of the mean. And if that difference is, that probability is less than 5%, you assume that if it's smaller than 5%, it's to a probability smaller than 5% different from the population mean. And this is essentially what you mean to quantify. So this distribution of the sample means actually allows you to characterize again your curve, and it's narrow and it's more likely to be a normal distribution. So you always find by utilizing this as a normal distribution, and assuming this is a normal distribution. So now this also allows for you to take out the skewness of your data, because your scores will likely be skewed. And then it allows you to do hypothesis testing. So again, you have now an M. So that's a sample mean. That's not a population mean. The population mean is here, mu. And you mean to, in the first attempt of hypothesis testing, the first test that we're discussing is the STAT test, where we're comparing the sample mean to the population mean. We're calculating a difference, and we're assuming that this is now that sample mean, that is the mean of mean calculated from repeated random sampling from your population. And we're building around the hypothetical standard error of the mean, which is calculated as shown here by a division of the standard deviation sigma by the square root of the sample size n. That means that essentially your standard error of the mean gets smaller because your denominator gets larger with an increase of the n. By making this smaller, you're basically increasing the probability that you get a larger set score. A larger set score, so if you have m minus mu, this is a difference. You mean to standardize this difference by utilizing the standard error of the mean, sigma m. So you're basically doing the same thing. And then you are quantifying the probability of this coming from the same or a different distribution by looking this value again up on the set score table. If your set score is greater than absolute 1.96, you have here was 1.96, you have here 2.5%. And you need to assume this to be basically double. So you have, because you have two tails, so you basically, you're taking 5%, which is 2.5% multiplied by 2, gets you this 5% alpha that we will discuss next time. So 1.96 is essentially that threshold of a set score where you standardized your distribution of the differences that will lead you to reject your null hypothesis that there's no difference between your sample mean and your population mean. If that value is smaller than that or larger than that, depending in which direction you're looking at it, which we will discuss on Wednesday, you're rejecting the null hypothesis. And in that context, Nolan and Heinzen just wanted to briefly talk about this, which is everybody wants the significant difference, right? So that means everybody wants essentially a set score or a p value corresponding with that set score that is smaller or larger, depending on which direction you look at, than 1.96. And what Nolan and Heinzen want to emphasize here is that the highest occurrence of set scores in the literature they found, according to a meta-analysis, which they're not citing, but it's a meta-analysis and that looked at this, is here around 1.96, which means everybody's trying to kind of squeeze their results to pass that threshold and kind of cheat their way into having a significant difference. We will talk about that more later on Wednesday. Essentially, we're going to talk more about this. The n is the sample size. So if you, I just want to repeat that quickly. So you have the standard error of the mean. So you basically, you pick random samples and you get one mean. You assume this mean to be the mean of means of these random samples, and you build around the hypothetical distribution of these means of these random samples. And that is quantified here by relating it to the standard deviation, where the standard deviation divided by the square root of the n, where a larger sample size diminishes and makes this standard error smaller, and thereby will allow you to get a larger set, which again will more likely result in a smaller p, which is more likely to make this a significant difference and for you to reject the null hypothesis. Yep. Thank you.
Thank you.
Have a nice evening. Yes.
Since when you sent out the rules, I wanted to look at my answers, but then when I went onto my Canvas, I just was looking to like see what I submitted. It's always saying I submitted part 2. I remember submitting 2 parts because I did it on 2 separate Excel sheets to keep myself organized.
Okay.
Is there a way to make sure that you got both my parts, like both things I submitted?
Well, if it's submitted,
Because it's only saying this one part, but I know for like I did this once for a different class, and just I think when I submit a second one, I don't get to see the first one anymore, but I'm pretty sure you still see both. I just want to
yeah,
make
I'm
sure.
only grading the latest submission.
What?
I'm only grading the latest submission.
No, but I'm saying if I submitted two things.
Okay. I should see both. Yeah.
Is there a way to
I
make
would-
sure? You'll look. Or should I send you an email?
Yeah, send me.
An email? Okay. Do you know how many questions? Oh, no, no. Do you know how many questions about the midterm's going to be on? Like 50, 40,
I think it's 20 or 30.
20?
It's not terrible. You even
Is it like-
I think it's 30. You have 2 minutes a question. It's 1 hour, and you have 30 questions. Yeah.
Here, thank you.
Sure.
Because I just want to, this is my homework one. The last modified is October 3rd. Like I haven't,
Okay.
that's when I submitted when I didn't do. I don't know, this is my first time. I want to make sure Canvas had it. But I can shoot you an email just to, I'm nervous.
Yes, please do. Don't worry.
But I have it. It's October 3rd. I just want to make sure you got it.
Okay, good, good,
Thank
good.
you so much.
Thank you.
Yeah, like, oh, I'm sure I can tell them, when it comes.
I have a question on the homework.
Yes.
I saw you posted like the solution, the answer to the first homework, but did you like actually grade the homeworks?
Not yet.
Okay,
I'm still working on that.
okay.
It's a lot of submission.
I'm sure, yeah.
No, no, no.
All right.
But don't worry, if you have a serious attempt, you can be fine. Don't
Okay.
worry.
Thank you.
Thank you.
Oh.
So Dude, it actually sounds so fun.
I come in,
Yeah, I love to.
because you have an intellectual, and I get on Tuesday with you or not.
Sophie,
I'm
I
sorry.
got so lucky to have my life.
Thank you, Professor.
Thank you. Bye-bye.
What do you have tomorrow?
I was like, doing my classes out here.
So I couldn't help you.